Hello and welcome, everyone. My name is Dane Menke. I am the Digital Marketing Director here at Regenesis and Land Science. Before we get started with the webinar today, I have just a couple administrative items to cover. Since we're trying to keep this under an hour, today's presentation will be conducted with the audience audio settings on mute. This will minimize unwanted background noise from the large number of participants joining us today. If the webinar or audio quality degrades, please try refreshing your browser. If that does not fix the issue, please disconnect and repeat the original login steps to rejoin the webcast. If you have a question, we encourage you to ask it using the question feature located on the webinar panel. We'll collect your questions and do our best to answer them at the end of the presentation. If we do not address your question, we'll make an effort to follow up with you after the webinar. We are recording this webinar, and a link to the recording will be emailed to you once it is available. In order to continue to sponsor events that are of value and worthy of your time, we will be sending out a brief survey following the webinar to get your feedback. Today's webinar will focus on lessons from the field from designing methane mitigation systems. With that, I'd like to introduce our presenters for today. We're pleased to have with us Matt Ambrusch, Associate Principal at Langan. Matt Ambrusch is an environmental professional with expertise in situ remediation and pneumatic remedial systems. His experience spans the entire remedial process, including the investigation and characterization of various environmental media, design, OM&M, and optimization of remedial systems, observation of remedial system installation, and preparation of reports, permits, and other environmental regulatory documents. His proficiency also extends to the testing, evaluation, design, and optimization of vapor intrusion mitigation systems, spanning traditional and innovative approaches. We're also pleased to have with us today Ryan Miller, Director of Land Science. Ryan Miller oversees the overall operations and strategic direction of the Land Science Division, ensuring the successful design, installation, and implementation of various vapor mitigation systems, including TerraShield, EverShield, MonoShield, and RetroCoat. He provides technical support, fosters collaboration, and drives advancements in vapor intrusion barrier technology. He has extensive experience in the environmental consulting industry, focusing on brownfield redevelopment projects and specializing in vapor intrusion mitigation. All right, that concludes our introduction. So now I will hand things over to Matt Ambrusch to get us started.
Great, thank you so much. And first, I want to thank Ryan and the Land Science team for giving me the opportunity to present today. Really appreciate it, and thank you to everyone out there for taking an hour out of their day to attend this webinar. As was mentioned, we're going to discuss today designing methane mitigation systems, and more specifically, looking at how they vary from the more traditional VOC-related type mitigation systems or radon systems, for that matter. Looking at not only how those design considerations are different for methane mitigation systems, but also giving everyone a flavor for some of the things that we've seen work well and not work so well, and site-specific considerations when designing these systems. So before we jump into it, just want to give everyone an idea of kind of what today's webinar might look like. First, we're going to just start with going over vapor intrusion mitigation objectives, probably pretty standard for most people on the call, but just want to level set everyone and identify, what we're typically looking to do when we're designing a mitigation system. We'll look at typical design considerations, and then we're going to jump into really the heart of the conversation, looking at how methane is different than typical VOCs or radon that might be mitigated, and then how we design differently for methane, looking at critical system components. And then finally, I'll hand it off to Ryan, and he'll talk a little bit more about some commercially available solutions in this space. So when we're looking to design a vapor intrusion mitigation system, the main objective, obviously, protect indoor air and be protective of human health. That's the main objective. But while we're doing so, we also want to consider a few other things, namely constructability, adaptability, and operability. So we could design the best system in the world, but if it can't be constructed, what good does that do us? Similarly, we want a system that's going to be able to adapt with changing site conditions or changes in the building footprint, whether that be during construction or post-construction as part of tenant improvements. And certainly don't have a crystal ball, but using some best management practices to design systems that can allow for a lot of the most common things that may happen during construction or post-construction. And then finally, operability. We want a system that's easy to operate, one that's intuitive, and one that allows us to adjust system performance as may be necessary based on, again, changing site conditions. And we're looking at all of this throughout the process of the design. So from pre-design through installation, we're considering all of these things as we move through the process. So when we're looking at designing vapor intrusion mitigation systems, we're looking at several different potential strategies. These strategies can consist of blocking, venting, pressurizing, flushing, or purifying. This is sort of a crude way of describing it, but I'll run through these quickly. We talk about blocking. It's a physical barrier to vapors making their way into the building, and that being vapor intrusion barriers. When we're talking about venting, we're looking at more traditional passive or active sub-slab mitigation strategies where we're preventing those vapors or mitigating those vapors from making their way into the building through either passive or active modes of depressurizing the sub-slab environment. When we talk about pressurizing or flushing, we're looking at ways of modifying the existing or new HVAC systems. So pressurizing, we would add a positive pressure to the interior of the building. So sort of alternative to when we're depressurizing the underslab, by pressurizing the interior of the building, we're mitigating the ability of those vapors to make their way into the indoor air. Also, you could consider flushing. So by increasing the air exchange rate within an interior of the building, we're not allowing any vapors that might wake their way into the building from accumulating at a level that's dangerous to human health. And then finally, air purification is more typically seen in a temporary condition, while a more permanent mitigation strategy can be put in place, but still an effective way. This being, we're not preventing vapors necessarily from making their way into the building, but more so purifying those airs, assuming that those vapors are in the building, creating a safe air for the occupants to breathe. Now, these mitigation strategies still apply in the case of methane mitigation, but as we'll talk about in more detail in this presentation, there are certainly additional components that need to be considered when designing a system for either methane or landfill gas mitigation. So again, these considerations, not specific to methane mitigation systems, but mitigation systems in general. First thing that we're going to be looking at are site conditions, and those site conditions consist of a number of different things, namely contaminants of concern and the magnitude of those contaminants, in addition to the depth of water. There are a number of other things that need to be considered, but these are sort of the main things, at least at the preliminary look, that we are considering when designing a mitigation system. And I've got contaminants of concern highlighted here in red because we're going to be discussing one contaminant of concern in particular today, that being methane. We're also looking at building type and the use, in addition to the size, looking at the site plan and understanding, is it a cut site, is it a fill site, and how those construction activities might impact the site conditions, contaminants of concern, and the potential for vapors to migrate into the building. We're also specifically looking at the structural, architectural, mechanical, electrical, and plumbing for the building that's to be mitigated. Our mitigation system needs to be designed in conjunction with these elements so that, again, it can be constructible, adaptable, and operable. And we want a system that's not going to impact the aesthetic or the functionality of the building that we're mitigating. So with that, now that we've run through sort of some of the baseline considerations for mitigation systems in general, I want to jump into methane, talk about what it is and why is it important and why are we talking about it today. So methane is a colorless, odorless, and highly flammable gas. The lower explosive limit for methane is 5% by volume, so not a huge concentration. The upper explosive limit being 15% by volume. And methane can exist at sites either naturally, through naturally existing organic matter, such as meadowmat, or it could be through the anaerobic degradation of solid waste in the case of landfills in particular. These are the most common sources that we see requiring methane mitigation systems in land development applications. So why is methane different than a typical volatile organic compound or radon? One being the acute health risk, and that comes in the form of the potential for explosions or fires. So if methane is present between 5% and 15% by volume, you've got oxygen, which I would hope you'd have in the building, and you've got an ignition source, you have yourself the potential for fire and explosion. In addition, as I mentioned earlier, one of the potential sources of methane in land development applications are landfills. And with landfills comes the potential for settlement. So that comes with itself a set of challenges that need to be considered when we're designing a mitigation system. And then finally, again, in the landfill application, there's a potential for other gases or constituents to be present as a result of the landfill, not just methane. And we have to understand how those other compounds may impact the functionality of the system and what other precautions that need to be taken to make sure that, again, the system's being protective of human health. The other thing to consider is that when we're designing a system for, let's say, radon or other VOCs, our primary objective is to prevent the intrusion of the gases from making their way into the building. However, with methane, there's a supplementary objective, which is to prevent or to mitigate the accumulation of methane from beneath the sub-slab. Reason being is, again, we don't want methane to accumulate beneath the slab to a concentration that could be dangerous from an explosion or a fire risk. Consider in the future if someone were to perform some tenant improvements, penetrate the slab, if concentrations of methane beneath the slab were to be within that 5 to 15% by volume, it could create a very dangerous situation. So again, same objective as a VOC system, which is mitigate the intrusion, but we've got that supplementary objective of preventing or mitigating the accumulation of methane beneath the slab. So if we were to look at a passive or an active mitigation system for the purposes of this presentation, the layout would generally, for the most part, look very similar. This is a system layout that we had for a very large warehouse in the Northeast, probably pretty typical or standard for most people on the call. You've got a series of vertical vent risers that manifold to a series of horizontal mitigation screens that are beneath the slab. And the idea, whether active or passive, is that those vapors collect via those screens, run through these horizontal header pipes, and then transition vertically up through the vent risers and are discharged above the building into the atmosphere. But as we'll talk about on some of the future slides, there are some critical components to methane mitigation systems that need to be considered. And as we walk through those critical components, we'll also look at some of the lessons learned when implementing such components. So I've gone ahead and grouped these critical system components into a couple of different key considerations, and we'll walk through these on subsequent slides. But we're looking at the potential for methane gas to migrate, whether beneath the slab or across the site. Again, this potential for settlement, the acute hazard that methane presents, and how do we monitor this effectively? And then finally, materials of construction. Again, and as we'll talk about on that slide, but looking at not only the constituents in the gas itself, but also the potential for settlement and migration and how that goes into particular materials of construction that are used. And as we'll see on subsequent slides, there's a site-specific basis for all of this, as is typical for any mitigation system. So I don't want to give the idea that all of these components are necessary for every methane mitigation system that's designed, but we'll do my best to identify in certain instances where they need to be considered. So the first consideration that we'll look at is migration. So similar to VOCs, there's potential for these vapors to migrate beneath the building or across the site. The difference is that the acute health concern that methane presents, it's important that we mitigate or control the migration of methane throughout the building or across the site as much as possible. So two such components that we typically include in our mitigation system designs, one being trench dams, the other being seal-off fittings. So trench dams, the idea is that if there are any utilities running across the site, they're typically placed in a high permeability bedding material as part of the design of those utilities. That high permeability bedding material, as folks can appreciate on this call, presents a preferential pathway for those gases to migrate. And particularly when the methane that's present is originating from our site, we want to be mindful that these utilities don't present a preferential pathway for methane to leave the site. So particularly in the cases of landfill redevelopment, there's a concern that if methane were to use this bedding material, these utilities as preferential pathways, methane could accumulate offsite and folks could unwillingly be introduced to or unknowingly introduced to elevated concentrations of methane in a dangerous environment. These trench dams really just a physical barrier, whether it be a bentonite or a grout slurry that's installed such that it intersects that high permeability material, creates a physical barrier for that methane to migrate offsite. And typically that is done near the property boundary to the extent possible. Seal off fittings. This is designed for any dry utilities that may penetrate up through the slab. The thought being is that these utilities running in the subsurface, if they were to be compromised or damaged in some way or have a loose fitting, there's a potential that methane might make their way into these utilities and be a preferential pathway. What we want to prevent is that methane, again, using that to find its way to um, electrical components within the building, accumulate, and again, create a very dangerous environment for electrical that's rated for a non-hazardous condition. So the idea is here, again, a physical barrier. There's several different types of materials that can be used, but effectively it's a seal within the conduit such that gases cannot migrate through that conduit. And this is done just inside the building above the building slab. A couple things that I'll note for seal off fittings, not overly common, but in some instances we do see this, that if these dry utilities are installed above the vapor barrier below the slab, there's a potential that we could consider doing without the seal off fittings, again, because that vapor barrier acts as a way of mitigating the vapors, and the need for a seal off fitting may not be as crucial. Again, that needs to be considered on a site specific basis. I will mention that these are not typical components of a mitigation system. So it's very common, if not discussed upfront with the entire project team during a kickoff, that these items are typically overlooked and are much more difficult to install after the fact, keeping in mind that while people may be familiar with implementing or installing mitigation systems, they may not have seen these elements, and identifying that upfront as part of the process is very important. The next component to consider is settlement. Again, this is typically associated with land development applications where landfills are present. And this is something that needs to be coordinated with the geotechnical engineer and structural engineer to understand the likelihood or possibility of settlement, and to the extent, the magnitude of settlement that's anticipated. But if settlement is anticipated, there are several different things that can be included in the design to allow that it to continue to operate effectively post settlement. A couple of these include pipe hangers. So these are elements that are installed prior to pouring the slab, and they become integral to the rebar of the slab, and they hang in place. So as the slab potentially moves, so too will the piping, and prevent any potential for pipe damage, or to the extent that it can, sloping or low points in the piping. Also, there are flexible joints that can be installed along with different materials of construction. So typically we would see PVC pipe be used beneath the slab for a typical mitigation system. HDPE pipe is another potential material of construction that can be used, that has a bit more flexibility, and again will mitigate the potential for damage of the pipe if settlement were to occur. We'll note that these elements do certainly add a time element to the installation as well as a cost. But again, keeping in mind that our ultimate objective is to be protective of indoor air and the occupants of the building, and also allowing it to be adaptable over time. We want to be able to install or implement measures that will allow the system to operate over time, regardless of way may happen as it relates to settlement. The next consideration is acute hazards that are related to methane. As I mentioned, it has the potential for being an explosive or a fire risk. So some of the ways that we can go about mitigating this, we'll start with indoor air sensors. So this is certainly something that's different, not part of a typical VOC related mitigation system. Certainly we would like to think that our mitigation system is going to prevent dangerous levels of methane from entering to the building and accumulating. However, we want to be sure that we're being protective of the occupants of the building. And if something were to go wrong with the system, that we're made aware of it. So indoor air sensors are a crucial part of a mitigation system targeted for methane. These sensors are installed approximately a foot from the top of the ceiling. And that being because methane is lighter than air and will accumulate at the top of the building itself or a ceiling. We typically include several set points to allow us to understand where the concentrations of methane may be and allow folks time to make necessary adjustments or arrangements to be protective of indoor air. Also, when we're talking about an equipment room where we might have equipment for an active mitigation system, we're typically looking to have a separate HVAC system for that particular room. Reason being is there is a greater potential for methane to be present within that room if there were to be a failure of that equipment. What we want to avoid happening is if you have the HVAC system associated with that room tied with the rest of the building, there's a potential that you could be quote unquote spreading methane across the building and creating a dangerous environment throughout the entirety of the building as opposed to a localized within that particular equipment room. And then finally, something that we would look at is this potential for hybrid system operations. Again, not something that's typical for a VOC system, but again, going towards the objective of both mitigating the intrusion of methane as well as the accumulation of methane beneath the slab, hybrid systems offer that ability. So systems would typically operate as a passive system. These systems would then be equipped with an inline sensor in that each individual vent riser. And if the methane gases that are passively being vented through that vent riser were to hit a certain unsafe level, it would transition automatically to an active system operation. This is done through a three-way valve. So this three-way valve is typically closed to the active equipment, open to the passive system. That inline sensor reads a methane concentration that's triggering. That automatically closes that valve to the passive vent riser, opens it to the active vent riser, and then activates the operation of the fan. And that fan will operate for a period of time until that concentration of methane in the vent riser is identified as being below the set point and at a safe condition, at which point the system would then automatically transition to passive mode via the three-way valve. Also, whether a hybrid or an active system for methane mitigation, the equipment needs to be intrinsically safe because it has the potential to be moving hazardous concentrations of methane, flammable concentrations of methane through the system. Those systems need to be intrinsically safe to be protective. Again, something different than you would see in a typical VOC type system. And as I wrap up the presentation this afternoon, I'd just like to run through some big picture takeaways before I hand it off to Ryan. As was discussed today, while designing methane mitigation systems, the concepts are similar to your typical VOC or radon mitigation systems. There are certain considerations that need to be taken into account in order for them to be protective of the occupants of a building, given the certain characteristics that methane present differently than VOCs and radon. Those critical system components need to be considered on a site-specific basis and need to be incorporated throughout the process such that the systems are constructible, adaptable, and operable, and ultimately protective of human health and the occupants of the building. With that, I'd like to thank everyone for their time today. Appreciate it very much. Look forward to answering any questions you folks may have. And with that, I'd like to turn it on over to Ryan. wrap us up.
All right, thanks, Matt. So like Matt said, I'm going to transition a little bit here. You kind of heard what goes into designing a methane mitigation system. I'm going to take a little bit of time, zoom in on kind of one of those pieces, which is the vapor barrier itself. So I'll spend a few minutes kind of focused on what the role of the vapor barrier is in the methane system performance, specifically how durability and QA/QC can contribute to the success of any given project that we're working on. So I'll start where we often start here at Land Science. If you've attended one of our webinars, you may be familiar with this, but we often kind of evaluate contaminant vapor barriers by really two primary criteria: chemical resistance, right? The ability of the vapor barrier to block vapors, and then what we call constructability. So, how easily is it installed? How durable is the vapor barrier? The overall quality of the installation. And it's really the combination of these two factors that will kind of determine which barrier makes the most sense for any given project that you're looking at. And so again, that first part that I mentioned, chemical resistance, a lot of us are familiar with this component, and Matt touched on it, making sure you have a vapor barrier that is compatible with the contaminant that you're dealing with. And in this case, it would be methane. And just as important as having a vapor barrier that is compatible with the contaminants that you're looking at, you also want to have a vapor barrier that is constructible, right? You could have the most chemically resistant vapor barrier in the world, but if it can't be installed properly, I think as Matt had referenced early in his presentation as well, what good is it doing you? So when we're evaluating kind of the overall constructability of a vapor barrier, we're looking at a couple different factors: the efficiency of the application, the ease of the installation, to the durability of the membrane, and then the third being the measures put in place to ensure that you have a quality installation. I'm going to spend a little bit of time focusing on the durability component of the vapor barrier. We see it often, the term kind of durability, that we use it a lot, and we mean a couple different things. So I think it would be helpful to kind of double click on what we refer to as durability and why it's important. So Matt showed a couple great photos during his presentation of some projects and installations. Here's another one. I think the common thing, these systems are being installed at active construction sites. And that's something to keep in mind as I go through this. So the physical properties of the vapor barrier then become really, really important. And so if we take a second to think about this question, why does durability actually matter? At the end of the day, the vapor barrier is one of the things that is separating that subsurface gas from getting into the building. And the unfortunate reality is it's getting installed during a very, for lack of a better term, abusive environment, right? An active construction site. The vapor barrier is getting placed over stone. People are walking on it and working on it. It can be penetrated from time to time. It's then covered and really never seen again, right? So once it's installed, we don't get a second bite at the apple. And so, durability becomes a very key part to that. And a lot of people kind of translate durability to mean thickness, and that is true to an extent, but durability also combines how the material handles stress, how it handles potential damage, how it performs at its weakest points, right? The seams and the penetrations. And so if we look at some of the physical properties that get built into durability, tensile strength and elongation are two important ones to be looking at. And they tell us how a material will behave when it's stressed, right? Can it stretch without breaking? Can it handle movement? So I guess that soil or slab movement, construction activity, because movement is going to happen either during the installation or over the lifetime of the building. You also have puncture resistance. So that's the ability to of the material to withstand damage or penetration. So you see these guys kind of working on the vapor barrier installation in this photo. You can imagine them working with rebar, carrying tools, things getting dropped on the vapor barrier or dropped and then dragged a little bit. So puncture resistance is another really important physical property characteristic to be looking at when you're evaluating a certain vapor barrier for any given project. Another physical property characteristic that is often overlooked, but it does happen, is the thermal expansion and contraction. So if you can imagine a vapor barrier being installed, it's seamed, it is terminated at the building edges, and if that vapor barrier is sitting out for a day and the sun is hitting it and it's not covered, certain vapor barriers will contract and they will bust at the seams and they will pull off the walls, and all of those areas need to be redone and resealed. So something to consider when you're looking at different vapor barriers on certain projects is the idea of thermal expansion and contraction. And so to kind of summarize some of these physical characteristics, again, tensile strength, elongation, puncture resistance, they all play a really important part in the performance of a vapor barrier. The one thing I'll note is understanding that the ASTM methods for these physical properties are not all the same. They are very specific to the material that they're being tested against. So there is not one correct method for puncture resistance. If you look at technical data sheets on a number of different vapor barriers, you're going to see a lot of different ASTM methods, and that's because the method is specific to the material. And another thing to kind of keep in mind, and this is kind of reiterating the point here, but physical properties are directly related to things that are happening. So the subgrade materials above and below the vapor barrier, the rebar or the other trades that are working on and around that vapor barrier, the pours, the concrete pours, the trucks that may be on top of the vapor barrier after it's installed, potential differential settlement, which Matt did a really nice job outlining. So all of these things kind of play a factor and why the physical properties are so important. The takeaway here is that there really is no one barrier fits all scenario. You should be looking at the contaminants that you have at your site, the concentrations that are at your site, what the building is going to be. Is it a corner gas station that's being turned into a convenience store? Is it a large logistics warehouse? The vapor barrier that's selected for those sites may be different. And then I'll kind of note here at the bottom, consult us as the vapor barrier manufacturer, consult Matt as the design engineer. We have a lot of knowledge and we see a lot of projects. And so we can kind of use that expertise to help guide certain decisions. And so just to take it a step further, how do we ensure a vapor barrier that we selected, right, after reviewing some of those important physical properties is actually installed properly? And that's by following a CQA, construction quality assurance, or a QA/QC plan. Now, this plan should include a number of things: manufacturer review, pre-construction meeting, certified installers, a third-party inspection, thickness verification of the vapor barrier during installation, smoke testing of the vapor barrier during installation, doing an inspection before the concrete slab is poured, being on site during the concrete placement. So there's a lot of things that should be included as part of a robust QA/QC plan. And so when I say kind of manufacturer peer review, that could be anything from helping lay out the venting to creating custom construction details. This goes back to what I was just saying on the previous slide. Take advantage of the historical knowledge and expertise that the project team can bring to the table. Pre-installation meetings, in my experience, this is one of the best things that you can do to ensure success in the field. And oftentimes it gets skipped. getting together the project team, whether that's the general contractor, the vapor mitigation installer, the design engineer, manufacturer's rep, the whole project team, if you can get them on site or at least on a call, will help kind of clear up responsibilities or scope or contingencies is a big one. If weather impacts the schedule, what are the contingencies that are in place? Getting all of this out before people are in the field is such an important step, as is using a certified installer. So experience matters, training matters, VI knowledge matters. If you are having a site contractor or a concrete subcontractor install your vapor barrier, their number one priority is the other scope, the site work or the concrete. When you have a certified installer on site, their number one priority is the installation of the mitigation system. Having a third-party inspector on site, it's really important for someone else to be there to just observe the installation, record site conditions, be involved in the smoke testing or the thickness verification, taking pictures. These are just really important things that should be documented and then plugged into some report so that there is documentation after the fact if there is an issue. I've mentioned thickness verification a number of times. This is specifically when installing a composite vapor barrier system. So if a composite vapor barrier system is designed to be 30 mil or 40 mil or 60 mil thick, whatever it may be, as the material is being sprayed out, you can cut a coupon out of the of what is installed and measure the thickness in real time. So if it's less than what is designed, well, you need to then come back and spray more. It's just a really good way to verify the right thickness is being applied. Smoke testing is also, in our eyes, an absolute requirement. There's really no better way to confirm that you have a vapor tight seal than conducting a smoke test. So the photo on the left there, the gentleman's sending smoke underneath the vapor barrier. And then the photo on the right, you can see some smoke coming out around the penetration. So in this scenario, we don't have a vapor tight seal, which can be common. But the huge benefit of doing a smoke test is you can see this in real time, come back, make the repairs, do another smoke test, and confirm that you have everything effectively sealed. So I'll wrap it up here with a couple takeaways. No matter what vapor barrier system you're installing, ensure that you have a QA/QC plan in place. It doesn't need to check off every single one of those components I just mentioned, but having a majority of those things put in place will really help the success of a project. And make sure that it's project specific, right? Again, the convenience store at a corner gas station is going to look different than a large warehouse. And the QA/QC plan may reflect that. A poorly installed vapor barrier really defeats the whole thing. I think that is obvious when you say it, but constructability is equally as important as chemical resistance. Going back to the initial slides, you really have to balance the combination of both of those things to make sure you have an effective vapor barrier. And then make sure your project team cares as much about the outcome of the project that you do, right? And that leads into utilizing the experience of a certified installer. They're there for a very specific reason to install a vapor mitigation system successfully. And you should be utilizing that experience. So if you want to learn more about any of our vapor barrier systems, TerraShield, EverShield, MonoShield that you see here, feel free to reach out to me or anyone on the land science team. We're always happy to talk with you about some of these options. Thank you. So if there's any questions, we will, Matt and I will be more than happy to take those.
All right, thank you very much, Ryan. Yeah, so that concludes the formal section of our presentation. So now we'd like to shift into the Q&A portion. Before we do this, just a couple quick reminders. First, we will be sending out a brief survey after the webinar. We really appreciate your feedback, so please take a minute to let us know how we did. And also, you will receive an email with the recording as soon as it is available. All right, so let's circle back to the questions here. We have a question from Matt. And Matt, the question is, how is the determination whether a hybrid system is warranted or not typically made?
Sure. Yeah. No, that's a great question. I think it can vary. I think one determining factor is the going back to what I had said earlier in terms of the source of that methane and understanding whether or not that source is consistent or going to be consistent over time, or if it's a more of a fleeting source. Also, the concentration of methane certainly, and the pervasiveness of across the site. So based on any maybe pre-investigation activities that had been done, understanding what those concentrations look like, and how pervasive they are across the proposed building footprint. All of those go into it. But again, thinking about the objective of the system not only being protective of indoor air, but also to mitigate the accumulation of methane beneath the building slab, it's important to consider the need for a hybrid system.
All right, thanks, Matt. So let's see. Here's another question, or here's a question. It's for Ryan. Ryan, what vapor barrier does Land Science typically recommend for methane?
So all of the vapor barriers that we offer at Land Science are compatible with methane. So if we're dealing with methane specifically, it's less so do we have one vapor barrier that will work better with methane, and more so what is the project, what is the building, what are we kind of dealing with that may dictate which vapor barrier system would be the right fit. So again, we always kind of look at the project specifics, the building type, the subgrade, the building foundation. All of those things are very important, in addition to, hey, we need to make sure that this vapor barrier is also compatible with methane.
All right, thanks, Ryan. Matt, question for you. What has your experience been with selecting or procuring vapor barriers for use in situations where methane is a contaminant of concern?
Yeah, no, I think Ryan did a really nice job outlining barrier selection there. To my point earlier in the presentation too, it's we want to be sure that when we're looking at particular barriers, we're comparing them apples to apples. So there's a couple of different ways to do that. One being, the transmission rate or the permeance value of a particular contaminant through that barrier. And to Ryan's point as well, looking at a number of other factors that are specific to the building construction, building use, building type. So looking at ease of installation, durability, these are all things that go into the selection of a barrier specific to methane. But when we're trying to compare apples to apples, all other things equal, we're typically looking at that transmission rate and wanting to understand how compatible that barrier is specific to methane. And not all manufacturers, in my experience, have a documented transmission rate to methane, although they may claim that they are compatible to methane. So that's an important thing to look at.
All right, thanks, Matt. So Ryan, here's another question for you. It's, do you recommend venting for every project?
So when we're dealing with methane specifically, I think the answer is yes. We typically defer to the design engineers like Matt and folks like that are really in on the design side of things. But I think Matt spoke about it really well earlier in wanting to avoid any accumulation below the building slab as well. And so having venting in place is a really important piece to that puzzle. So the short answer is yes. When we're dealing with some of the other projects that maybe are more on the preemptive side and not related to methane, we do from time to time see projects that are not using venting and then installing just a vapor barrier. But those are very specific projects that are dealing with kind of the preemptive nature of not having any documented contaminants on the site, but wanting to put something in place.
All right, so let's see. Here's another question for Matt. Have you had any issues with false alarms with indoor air sensors? And if so, have you how have you dealt with that situation?
The answer is absolutely yes, and it's a good point. And like any sensor, it is in some ways prone to interference and just basically calibration creep. So typically, manufacturers will recommend that there be bump testing or calibration done on those units at least twice a year. Even still, there's a potential that whether again there's an interference with something else inside the building or just a sensor malfunction, there's a potential for false alarms. Now, our set points are a bit conservative to allow folks time to, as I mentioned before, take steps to make adjustments as necessary to be protective. Typically, we're doing a sort of a warning alarm at 10% of the LEL, and then we're doing an evacuation alarm at 20% of the LEL. Some things that we've gone ahead and tried to prevent the occurrence of false alarms. We add a delay to the sending of that alarm. So you will sometimes see a fluctuation at the sensor itself. What we want to make sure is that the reading at the sensor is a consistent reading, is not a fluctuation. So sometimes we'll put a 5 or 10-minute delay on that, and the sensor must withstand that concentration or greater for that period of time before sending out an alarm. So that's one engineering workaround that we've seen be effective to prevent some of the noise that might be occurring just due to the fact that sensors will be sensors.
Okay, thanks, Matt. Ryan, another question. Where do you see the most problems occurred during the application?
Yeah, so during the application in field, I assume this question means when the vapor barrier, vapor mitigation system is being installed. There's a number of things, but two jump out to me. One being elevator pits. Oftentimes, a project is requiring a vapor mitigation system, and when it kind of gets in front of everyone and they realize they need to install a vapor barrier, the elevator pits were poured 2 or 3 months back and did not include any vapor barrier mitigation below those elevator pits. So kind of going back and dealing with elevator pits is something that we see all the time. We do have options and solutions to kind of rectify those situations if they occur. The other place we see a lot of pain points is around sequencing of the vapor mitigation system and how it fits into the overall construction. As the general contractor is working on site, there's other trades working on site, and just getting the sequencing down right is kind of one of those pain points. But if you go back to what I said initially and have one of those pre-installation, pre-construction meetings, it can be solved before it even becomes an issue. So I'd recommend kind of keeping those things in mind.
Okay, thanks, Ryan. Matt, another question for you. How does the source of methane potentially change the way you may go about designing the mitigation system?
Yeah, I think one of those is just understanding the longevity. Methane is going to be present if it's due to organic matter beneath the building versus maybe a closed landfill at the end of its life. Understanding the concentrations and the longevity of those concentrations, that certainly goes into it. I talked a lot about too the development of former landfills and the considerations or the challenges that go along with that. So, if it is related to a landfill, we've got to consider things like settlement, the potential for other constituents that may be corrosive in some instances, those being present. So there are a number of other things that go along with mitigation systems associated with landfill redevelopment as opposed to maybe a natural source of methane.
All right, thanks very much, Matt. So that's going to be the end of our chat questions. If we did not get your question, someone will make an effort to follow up with you. For more information about environmental services from Langan, you can visit langan.com. And if you would like to learn more about vapor intrusion barrier technologies from Land Science, please visit landsciencetech.com. Thanks again very much to Matt Ambrusch and Ryan Miller, and thanks to everyone who could join us. Have a great day.